Hello, everybody, and welcome back for Unit 2. I hope you have been successful in your very first unit of your advanced geometry class. I'm super excited for us to move on now and get into some new topics. Unit 2 can be a struggle, so I want you to hold on tight and go for the ride and make sure if you have any questions, you get those answered right away. I am walking around the room as you speak, maybe unless you're doing this at home. In which case I'm not walking around your room, but I will please make sure you get some answers for the questions that you might have. All right, inductive reasoning is where we're going to be starting. What this is are reasoning based upon patterns that you are observing. So you have been probably looking at patterns in the past, probably even starting earlier as elementary school, but what you didn't realize is there's a name for that kind of reasoning that you were using to come up with the following numbers, and it's actually called inductive reasoning. So we're looking at patterns most often in numbers. Sometimes we do it in shapes, and very often you can look at it in graphs. But you are using inductive reasoning. So let's look at a couple of examples like that. We're going to look for a pattern, and we're going to try to find out what are the next two sequences that are in, next two numbers in that sequence, excuse me. So our first one here is with numbers. I have 3, 9, 27, 81. Now, whenever I approach these problems, I always think to myself, well, I could either be adding something to everything or probably multiplying something by everything. Okay, so when I look at it, those are the two things I look for. Sometimes it's different. Sometimes there are letters involved, in which case you want to look at the alphabet. Sometimes you are not going up by adding or subtracting or multiplying or dividing. In case it's going like the perfect squares. Like if I gave you 1, 4, 9, 16, you should be able to recognize those as your perfect squares. However, in this case, just to kind of keep it simple for us, I'm recognizing here, all right, well, if I look at the 3 to 9, I'm going up by 6, but to go from 9 to 27, I'm going up by more than that. So I know I'm not adding something. So then let's look at multiplication. Well, to go from 3 to 9, I would multiply it by 3. Well, does that work for the rest of them? It sure does. 9 times 3 is 27, and 27 times 3 is 81. So what I'm doing is using my inductive reasoning skills, and I'm noticing that each term is being multiplied by 3 from the previous term. So now I'm going to continue that pattern to get the next two terms in the sequence. So 81 times 3 is 243, and 243 times 3 is 729. Now we can also do this with a picture. Again, you probably have done something like this in the past. So let's take a look at what I have going on in the picture. Sometimes it's very obvious, sometimes it might be very slight. Okay, in this case, hopefully it's a little obvious to you. I see they're all circles, so that's one thing I am noticing. Every single thing has a circle, so I know my answers have to have circles. What's going on the inside? Well, the first one has a triangle, the second one has a square, and the third one has a pentagon. So I'm going from 3 sides to 4 sides to 5 sides. So what I'm noticing here is that it is increasing by 1 every time. So each circle contains a polygon, that's the important part, and has one more side than the previous one or preceding one. And so what I know is that the next one is going to have 6, and then the following one is going to have 7 sides, or hexagon and heptagon. And so do your best when it comes to drawing these things. Like I said, I am no artist, so just do your best, and it'll look something like this. So we can not always find ones that are immediately right after that, and so we might need something that's way farther down. These problems here, I wanted to find the immediate next two sequences. But what if I wanted to find like the 50th term? So it might be necessary for us to come up with something called a conjecture. And this is a conclusion you reach using inductive reasoning. Often, more than not, we're trying to look for a pattern to come up with a formula. Sometimes there are no formulas, and that's fine. But let me show you what I'm talking about. Okay, so in this example here, I want to make a conjecture to make about the number of regions 20 diameters form. So I'm trying to come up with a formula to use. Now, what do I mean by that? Well, if I had a circle and I drew 1 diameter in, I'm going to be getting back 2 regions. Okay, see how that's split up there? So can I go through and draw all 20 regions? Sure. But I would like to make it easier. Mathematicians are typically lazy and want to come up with shortcuts. So let's see what we can do. Well, if I do 2 of them, I'm noticing I now have 4 regions. Okay, well, how about if I do 3? I'm noticing I have 6 regions. So what I'm seeing here is that there is a clear pattern going on. 1 diameter forms 2. 2 goes to 4. 3 goes to 6. And what I see is that the number of regions is equal to the number of diameters times 2. So I can say R, hold on, make sure I got my pen. I can say R is equal to the number of diameters times 2. And by making this specific conjecture, I can now tell them what the 20 diameters would form without drawing all of them in. In this case, I would be doing 20 times 2, and there would be 40 regions in there. I don't know if I could ever draw a circle that's really small like these and get 40 regions within there. Maybe you can. I don't know. All right, moving on. We might need to look at things with patterns, and you might need to get a little bit, these are a little bit more difficult. For example, here, Coach Schatzer forgot to make plans for the day, so he asked all his students to find the sum of the first 30 even numbers. I don't know why he's doing math in his class, but, you know, to each his own. We want to make a conjecture and find the sum of the first 30 even numbers. So what that means is I'm looking at what is 2 plus 4 plus 6 plus 8 and so on until we have 30 numbers added together. So what we want to do is create a chart. On the left-hand side, I'm going to say, well, how many terms are involved as I'm adding? And I want to kind of increase by 1 every time. And on the right-hand side, I'm going to say, well, what's the sum? Because that's our goal here. That's our focus here, is what is the sum of the first 30? Well, to get the first 30, I might need to look at the first 3 or 4. So let's first start with if there was only one term. Well, the very first even number is the number 2. There's nothing to add it to, so that is equal to 2. If I now go to 2 terms, well, now I'm going to do 2 plus 4 for a total of 6. If I do 3 terms, 2 plus 4 plus 6 is 12. Continue on to 4 terms and 5 terms, I get 20 and 30. So now what I'm looking for is a pattern in the numbers here on the right-hand side. I got 2, 6, 12, 20, 30. So like I said before, sometimes you're going to want to look for adding and subtracting or multiplying and dividing. Well, to go from 2 to 6, I would add 4. But 6 to 12, I'm not adding 4 again. So it's not an addition pattern. To go from 2 to 6, I'd multiply by 3, but 6 to 12, I would not. So again, it's not a multiplying. So when this happens, you're going to want to break down those numbers and see if there's actual patterns within those numbers there. For example, the number 2. Well, what do I know about the number 2? 2 is made up of doing 1 times 2. Okay, so let's move on to the next one. I have 6. Well, if I have 1 times 6, that's really not going to help me much, but I can see I got 2 times 3. Interesting. I have 1 and 2. Those are right next to each other. 2 and 3 are right next to each other. Can we do that with 12? Well, 12 is 3 times 4. That's happening again. And now we're increasing. 4 times 5, then 5 times 6. And this is now a clear pattern to me. The first thing I want to point out is this guy right here, this very first column. 1, 2, 3, 4, 5. Remember back over here where we talked about the number of terms? Terms 1, 2, 3, 4, 5. We have that number right there. This second number here, I can see is taking that number and increasing it by 1. Okay, so my conjecture is each sum of consecutive even numbers is the product of the number of terms and the number of terms plus 1. So in this case, I'm taking the number of terms n and this second number n plus 1. And that's what I'm going to be multiplying together. So for this specific example, I'm going to do 30, and then 30 plus 1 is 31. So 30 times 1 is 930. Okay, so this one was a little bit tough, and I completely understand that. You just got to persevere and work through it. And if you have any questions, please just let me know. Write them down now, and we'll come back to them. So let's take a look at it when we're using, say, graphs. So we've done a couple things. We've looked at, the pattern words right next to it, and we made conjectures about pictures and about numbers. So now let's look at graphs. And you probably, again, have done this in the past. We're looking at patterns based upon what has already happened here. This is referencing sales of backpacks at a nationwide company, and it's decreasing over 6 consecutive months. And we want to make a conjecture about the number of backpacks the company is going to sell in May. I don't have that information on here. So this is kind of similar to the first couple of problems that we were doing and looking at the patterns. And I want to kind of figure out, well, what is my pattern? And what I'm noticing is that it's kind of falling down in a straight line in this direction here. And it's almost kind of doing it at about 500 each. Okay, so when I hit May, I'm at April right now, I'm going to go down another 500. So I'm at 8,500, so now I'm going to go down another 500 to get 8,000 backpacks. So that's kind of where my prediction is going to be. Now, if I were to continue this on to June, it probably would make sense to go down even further. And it's going to be about, I would say, 7,500. Again, using that same exact conjecture I did before. It'll probably be a little bit more than that, meaning like a bigger number jump down, because June is the end of school and people don't typically get backpacks then, but we're using our original conjecture. Now, what I want to know is that as reasonable to use to make a conjecture about August? And what I want you to think about is what happens in August. Well, unfortunately, many of you go back to school at that time. And so in that case, odds are many people are actually purchasing that. So it is not reasonable to use this graph, but instead something where it would be more yearly, okay, sold in on a yearly pattern. Okay, so let's just take a break and look at some interesting facts about Sherlock Holmes. I don't know if you know who he is, but he is a famous character in the Arthur Conan Doyle stories, or some of you might know him from the show Sherlock. But he is often saying that he is using science of deduction. But really, we want to know, is that what he is doing? You know, he goes through and he looks at a crime scene, he looks at the details of the scene and the victim, and he kind of makes conclusions from that. But really, he is making conclusions about information that he is observing to make conclusions, even that they have not been observed. You know, for example, he looks and he sees maybe there's a woman on the ground who's died of natural causes, or maybe that she was murdered or fell through the ceiling from an airplane flying 1,000 miles above. But he doesn't really know. So instead, he's looking and he's making some observations, like there's a cigarette on the floor, or so that's possible that she probably didn't fall from a big height, or there's broken glass somewhere. So that means it could have already been broken when she got there, or there might have been broken in a struggle. Or does she have any lacerations? Is her dress damp from the rain outside, or is it dry? And he goes on to gather some information until he comes up with a conclusion. Now again, there's no fact there, and that's what deduction means, is to come up with using fact. So really, he is not using the science of deduction, although he might a little bit, but for the most part, he is using inductive reasoning. So really, here's our the science of deduction for Sherlock Holmes. We need to make a little bit edits, as you can see right here. I decided to edit it for him. We need to utilize inductive reasoning to formulate probable solutions, opposed to deduce everything there. All right. But the big thing here is not everything that is going to be said to you is true. That's something you have to kind of keep in mind. And when that happens, we can make something false by coming up with a counterexample. And that's an example that shows that a conjecture is incorrect. So you could say something to me, but if I can prove it wrong by using a counterexample, then you are incorrect. The big thing here is you only need one example to disprove a conjecture, but you need to show every case to prove it. Okay, so as long as you can come up with one thing, then you're good to go. So here's our last example. We're going to do 3 of them. We want to find a counterexample if it exists. For example, if the name of the month starts with a J, it is a summer month. Well, we do have June, and we do have July, but we have January. January starts with a J, and that is found in our winter month. So that is a counterexample for my conjecture that if it starts with a J, it's a summer month. Second one, you can connect any 3 points to form a triangle. So most often than not, if there are 3 points, we can put them together to find the triangle. However, what happens if it is a straight line? So that is an example here where it is actually not able to form a triangle. And my last here, when you multiply a number by 2, the product is greater than the original number. So thinking about it, yeah, 2 times 3, that's 6. 2 times 4, that's 8. Oh yeah, definitely, everything is getting bigger and bigger. But what if I multiplied it by a negative? If I did 2 times negative 4, well, now we're going down to negative 8. So that number, that resulting number, the product, negative 8, is definitely smaller. Or if I did something like with 0, and I multiplied it by 0, it's definitely going to be smaller. Okay, so these are just examples of inductive reasoning, and here are some conjectures that have been made with a counterexample. So moving forward, as you're making your conjectures, if you can come up with a counterexample, you need to go through and look at it again. That's it for today. Let me know if you have any questions.